Hey guys, welcome back to chapter 13. What we're going to talk about in this video is we're going to continue this idea of solubility. So looking at the process and really focusing in on this endo and exothermic process. And then we're going to talk about a few factors that affect solubility one way or the other. So just as a reminder, here is that solution process that we introduced in the last video. So we had 3 steps, if you will, that we had to consider. So the first step that we had to consider was this solute interaction. So we had to overcome lattice energy. We had to break apart that solid in order to make room for the solvent. Step 2 was this solvent interaction. So again, those are attracted to one another, of course. And we've got to break apart that interaction to make room for the solute particles to come in. And then this third was the solvent solute. So this is our payoff, right? So that was the one that was an exothermic process. By mixing those two together, we get large amounts of energy released. Okay. So let me talk about 2 different scenarios. So if I were to walk into my lab, pour a beaker of water, and then I were to add some sodium hydroxide to that beaker. So I add some sodium hydroxide to the beaker. Sodium hydroxide dissolves. I touch the beaker. It's going to feel hot. It's going to feel warm. Okay. So what does that mean? Well, when that dissolved in that beaker, that was an exothermic process. And it released energy during that process. And so when I put my hand on it, I feel that energy coming out. It feels hot. I can do the same thing with ammonium nitrate. So I can take a beaker of water, take some ammonium nitrate, pour it into the beaker of water, and then I touch that beaker, and now the beaker would feel cold. So what's going on there? Well, mixing ammonium nitrate in water is an endothermic process. So as those 2 are mixing together, it's stealing energy from its surroundings. It's stealing energy from the room around it. Or when I put my hand on the beaker, it's stealing energy from my hand. So my hand feels cold, but really what's happening is the heat is leaving my hand and going into that beaker. So what causes one of those to be exothermic and hot beaker? What causes one of those to be endothermic and a cold beaker? So let's look at this process. Let's break it down. Super busy slide. I want to break this down step by step. So bear with me here as we break this busy slide down. The first thing we're going to do is we're going to start right here. So this is our starting point. This is our starting line. So we've got our solvent in one beaker. We've got our solute in the other beaker. So step 1 is to separate the solute particles. So instead of having this crystalline structure, we break it apart to make some room for the solvent to get in there. In order to break apart those interactions, we know that we're going to have to put energy into the system. It's an endothermic process. So that's why we have low energy here. I'm going to have to add energy to climb up the ladder to get my solute separated. Okay, so that's step 1, putting energy in to separate those particles. Step 2 is separating the solvent particles. So I'm here, and again, to break apart the solvent to make space for the solute particles to come in. We know that's an endothermic process. We have to add energy to the system. So we go from low energy up to high energy. We have to put energy in to climb the ladder. Once we're up here, we're super duper unstable, right? So think about potential energy. If you're on the top of a mountain, that's really unstable. So up here is an unstable situation, but it's somewhere where we had to get before we can mix them together. So we've got our solvent separated, solute separated. When we mix these 2 guys together, we get our payoff. So when we mix them together, we are going to get a huge gain in stability. We're going to get a ton of energy released. So mixing solute solvent particles is going to be an exothermic process. High energy state, low energy state, energy exit the system to get that. Okay. As long as our landing pad, our final spot down here, is lower than where we started, and it in fact is in this case, we would see a net exothermic process. So we pay a little bit up front, but we get a huge return on our investment. And we have a net gain. So energy would be exiting the system into our bank account, if you want to stick with the investment analogy. So it's an exothermic process if the total energy cost for breaking attractions is less than the total energy released when we make the new attractions. Okay. So if the cost is less than the gain, we're going to have a net exothermic. Energy is going to exit the system. All right, so we're going to look at a very similar picture, but we're going to look at an endothermic. Okay, so again, here, we're starting. Here's our starting point here. We've got our solvent, our solute in beakers. So step one is going to be separating the solute particles. So overcoming that lattice energy, that's an endothermic process. We have to put energy in. So step one is climbing the ladder. Our solute is separated. Step two is separating our solvent. So separating those particles, making room for the solute. That's going to cost us some energy as well. So this is an endothermic process. We have to put energy into the system. So again, we've got this high energy situation up here where we've got separated solvent, separated solute. We pour one beaker into the other, we're still going to get a huge release of energy. So as those new attractions form, it's going to release a ton of energy. So super high energy states, we're going to fall down to a lower energy state. But what we notice here is that our landing pad is still higher in energy than where we started, right? So even though we got a return on our investment, we didn't get all of our money back, right? So here we would see a net loss of energy, or this would be net endothermic process. At the end of the day, we would find ourselves having to put energy into this system to make it continue to happen. Okay, so this would not be a good investment if you were in the banking world. So put money in, we get a little return on our investment, but when we calculate it at the end of the day, there was a net loss. We put more money in than we got out. Okay. So this is an endothermic process if the total energy cost for breaking attractions is greater than the energy released when we made new attractions. So we had to put more money up front. We get less money out on the other end. It's going to be an endothermic process. Okay. So as I said before, this isn't how things happen in reality, right? So it's not that we pull these apart first and then we pull these apart and then we put them together. And it's not really that simple 1, 2, 3. These 3 steps kind of all happen at the same time, and they actually happen in a very dynamic back and forth scenario. So let me just show you real quick a picture of what reality looks like. It's messy because that's what reality is. Let me show you just real quick what a picture of reality looks like so that you can see that this is applied to a very messy situation. So here's scenario 1. So scenario 1, we've got our water in the beaker. We've got our nice tightly packed sodium chloride molecule. So when I first add this sodium chloride to the beaker, there's only one way for this to go. The only way that this can move is sodium chloride breaks up, water solvates those ions, okay? We can't make any more sodium chloride because there's nothing in solution to add to this. So there's only one direction it can go, and that's to break up. So here we see the solution process happening. So the water molecules are breaking apart. The sodium chloride is breaking apart. and we see this solvation process happening. Then we're going to reach this place called equilibrium. Equilibrium is an idea that I introduced last chapter. I'm going to introduce it this chapter. And then the entire next chapter is all about equilibrium. So let's just talk about it real quickly again here. So this idea of a dynamic equilibrium is there's going to be a case where there's particles that are dissolving into solution. And there's actually also going to be particles that are recrystallizing onto this sodium chloride solid at the bottom. So we're going to have dissolving, recrystallizing, dissolving, recrystallizing. So that's where the dynamic portion of this definition comes in. Both are happening back and forth. This idea of equilibrium means that the rate of dissociation and the rate of recrystallization is going to be equal. So if I were to take a snapshot at 3 different moments, the amount of dissolved and recrystallized is always going to be the same. It just means different particles are coming and going at the same time. So that's the idea of an equilibrium. So what this is, what I put this up here to show you was just that this isn't a 1, 2, 3 process. It's not that simple. It's a very dynamic, fluid process that happens all at once. We have to consider those 3 steps during this very messy situation. Now we're going to move forward into something a little bit easier, a little bit more intuitive. So we're going to talk qualitatively, so in the absence of numbers, we're going to talk qualitatively about properties that affect solubility. So how can we increase the solubility, get more of something dissolved? Or how do we decrease the solubility where less gets dissolved? So that's the next thing we're going to talk about. We're going to talk about 2 properties. So we're going to talk about how temperature affects solubility. And we're going to talk about how pressure affects solubility, okay? When we talk about temperature, we're going to talk about how temperature affects a solid being dissolved. We're going to talk about how temperature affects a gas being dissolved. When we get to pressure, we're just going to focus on gas, okay? So solubility of a solid and temperature. What we see here, let me just quickly walk you through this table. So along the bottom here, as we go from left to right, the temperature increases. And as we go from the bottom to the top, solubility increases. So something down here, 10 grams would dissolve in 100 grams of water. And something up here, 90 grams would dissolve in 100 grams of water. So more would dissolve up here, less would dissolve down here. So we increase solubility as we go up the table. One of the things to notice about all of these, so these are all solid ionic compounds, so solid ionic compounds. One of the things to notice here is that all of these slopes are positive. So the big take home is as we increase temperature, solubility increases. Increased temperature, solubility increases. Increased temperature, solubility increases. So temperature affects them at different rates, that's for sure. But all of them have a positive slope. So as we increase the temperature, the solubility of a solid will always go up. What's an example of this, a tangible example? If you've ever made sweet tea here in the South, you put some sugar, a lot of sugar, into your tea, and you mix and you mix and you mix and you mix. Then you see that some of the sugar is just sitting at the bottom of your tea. And you're like, no, no, no. All of that sugar needs to be dissolved in my tea to make a proper sweet tea. So what do you do with that tea and sugar? You heat it up, right? So you heat up that tea, you start stirring again, and what you'll see is instead of the sugar settling on the bottom, all of a sudden, poof, it disappears into solution. So by increasing the temperature of that tea, it was able to take on more sugar and make proper Southern sweet tea. So that's just a tangible example of how temperature affects the solubility of a solid. So temperature goes up, solubility of a solid goes up. Now let's talk about the solubility of a gas and temperature. So I want you guys to all picture boiling a pot of water. So you put a pot of water on the stove, you turn it on, and it starts to heat up. Before you get that like rolling boil, like the actual boiling, what you'll see is little bubbles start to form on the bottom of that pan. They look kind of something like this. So those little bubbles that form on the bottom of your pan are nitrogen and oxygen and other gases that are trapped in that water. As you heat up that water, it can no longer hold on to those gases. So those gases fall out of solution. And so they come crashing out of solution, and that looks like bubbling up out of the solution. So what that tells us is that the solubility of a gas goes down as temperature goes up. So when I heat up that sample of water, it can't hold on to that nitrogen and oxygen anymore, and it lets it fall out of solution. It bubbles out. Okay. Another tangible example of this, so here's a graph. Let me just quickly go over this. So again, temperature increases left to right. Solubility increases bottom to top. And what we see, these are all gases over here. What we see is as we increase temperature, the solubility of all of these gases goes down. So another example of this idea of solubility of a gas and temperature is pouring warm soda versus cold soda. Or if you've ever worked in a restaurant industry and you think about a beer tap or even a soda tap, a warm tap versus a cold tap. So when you pour cold soda into a glass or cold beer out of a tap, what you see is the bubbles tend to stay in solution. So I pour a cold soda and I don't see a whole lot of bubbles form on the top. Some of it crashes out, but most of it stays in there. If you were to pour a warm soda into a cup or pour warm beer out of a tap, what you'll see is a lot of those bubbles come crashing out of solution. You're going to get a lot of bubbles on the top here. Nobody likes a ton of bubbles on the top of their soda or on the top of their beer. It makes it taste flat because now the gas isn't dissolved in the solution anymore. So this is why we always pour out of a cold tap rather than a warm tap, because we want our gas to stay dissolved. We don't want the bubbles to come out and sit on the top of our beverage. Okay. So that's solubility and temperature. The last thing we're going to talk about is solubility and pressure. So if I increase pressure, decrease pressure, what's going to happen to the solubility of a gas? So the example of gas and pressure, if we think about soda, okay? So soda, when it's closed, is a pressurized system. So if I have a closed can of soda or a closed bottle of soda, the pressure inside of there is higher than the atmospheric pressure around it. So that's a pressurized system. The pressure is higher inside. When I open that can or I open that bottle, what happens is the pressure dramatically decreases. So instead of being high pressure, it all of a sudden becomes low pressure. So opening the bottle, opening the can lowers the pressure. Well, what happens to the gas that's dissolved? The gas comes crashing out of solution. So this is just a little dramatic here, but you can see it. This is a little bit more realistic. So when you open that can of soda or you open that bottle of soda, you'll see the bubbles start to crash out. What does that look like? It looks like all those carbon dioxide bubbles coming from the bottom of your container and floating to the top, right? Or you feel or see that little gas kind of spray out when you open up that can. So what this tells us is that the solubility of a gas in a liquid is directly related to the pressure of the gas above that liquid. So long story short, increase the pressure, increase solubility of a gas. decrease the pressure, decrease the solubility of a gas. So I really like this kind of cartoon picture here. So what we see here is that here's our pressurized system. The can is closed. And we see the carbon dioxide, if we were to peek in, we'd see the carbon dioxide is dissolved in solution. So we wouldn't see any gas bubbles here. We would just see a liquid. When we open up that can, so pressure is released, all of a sudden the pressure drops inside of this can to match the atmospheric pressure. And what we see is the carbon dioxide is still in there, but now we see the bubbles rising to the top and dissolving out of that solution. So decrease the pressure and the carbon dioxide comes crashing out. Okay. That's it on solubility. Moving forward in this chapter, we're going to get into colligative properties. So tighten up on solubility because we're about to move on to something a little bit different in this chapter. I hope you guys found this helpful.